So today, I gotta like clutch up and start reading this, and then I'm gonna be going back to some punt engine stuff. Let's move this was term, cd punt. So then after that, what's the diff here? Just deleting stuff. That's because I moved it into here, right? So after that, I'm gonna be trying to figure out this system Verilog, Verilator stuff. I kind of just like jippity BS'd this like C++ part. Yeah, I've never used it, so we're gonna try to make it work for this moving average accumulator for punt engine. First, you know me, gotta blow up the bathroom right quick. One sec. Ладно. It's actually a pretty nice day out today. Got this like casual little rain. Shout out rain. Lastly, before we start, shout out Ghost, not sponsored. Just a little the bevs of the day. Shout out water. But yeah. Alright. So this is on well, I mean, I guess I can just read. It says dealing with cache misses in the processor pipeline. So let's just do this. So memory accesses disrupt the smooth operation of the processor pipeline. True. Therefore, we need to mitigate the ill effect of misses in the processor pipeline. It's not possible to mask a miss in the instruction fetching stage of the pipeline, but you can hide the miss in the mem stage. So here we have a read miss. So we are loading from A. And then 4 instructions later, we are reading from A again. Is that problematic? Suppose the LD instruction results in a miss in the D cache. The CPU stalls the load instruction in the mem stage, so the memory responds to the data. However, I5 is the instruction that uses the value loaded into R1. So yeah, we're stalling for this, but we don't even need that. Like we could just run these while we're stalling for that. It's the issue. So what does that entail? Chapter 5, we introduced the idea of a busy bit with each register in the register file for dealing with hazards. Busy bit for dealing with hazards. I don't really recall that, to be honest. We introduced the idea of a busy bit. What does that do? Yeah, I don't remember that for all. You can just relearn that. For instructions that modify a register value, the bit is set in the IDRR phase. And cleared once the write is complete. I'm gonna need some more elaboration on that. Write miss in the mem stage. So if it's write through, then we're also writing to memory every time we write to the cache. Cache block allocation policy is a no write allocate. The cache block allocation policy is a no write allocate. And the pipeline will not incur any. What is no write allocate? In a way, I'm clicking on LinkedIn for information. So what's the other option? Write allocate. So it's only reads that bring it into the cache. Execution time is equal to the number of instructions executed times the clock cycles per instruction average plus the memory stalls average. So, I guess that assumes you're not counting the memory stalls in the CPI. Times the clock cycle time. Effective CPI of the processor is the... Yeah, okay. I would have said that was in the regular CPU. The total memory stalls experienced by a program. Well, yeah, that doesn't make sense. Yeah, I'm bugging. Total memory stalls is the number of instruction times the average amount of memory stalls. I believe that. And the average amount of memory stalls is the misses per instruction times the miss penalty. I don't really like that much. This one. Let's do this. Consider a pipeline processor that has a CPI 1.8 without accounting for memory stalls. iCache has a hit rate of 95%. The Dcache has a hit rate of 98%. That's pretty good. Is that reasonable? It's kind of crazy. Assume that memory reference instructions account for 30% of all instructions executed. 80 loads, 20 stores. Dude, what is this program, bro? On average, the read miss penalty is 20 cycles and the write miss penalty. Effective CPI. So, effective is equal to CPI AVG time. No, plus mem bubble. Okay, I see here it says called mem stalls. AVG. So what is CP AVG? After 1 point, so that's 1.8 plus. So the average amount of memory stalls. I don't know if the cache part matters. I guess it does. So the read miss penalty, so loads, so 80% of the, this is actually so it's 30% of instructions. Yeah, I don't understand that how you do it 2 caches as well. So, cost of instruction misses. iCache miss rate. Oh, instruction cache and data cache. I forgot that was a thing. Yeah, it's fair. Exploiting spatial locality to improve cache performance. Tag cache index. So the tag is like the modulus. Cache index is like if you have like qn plus r. Cache index is q. This is r. And this is like a layer within that. Once you find n. N consists of block size block. N is a block consisting of block size addressable locations, and so the offset. So what is your mate with a qn plus r? Quotient, remainder. Quotient, remainder, and I would still call this an index. They're all effectively an index. I don't know. Whatever, it doesn't really matter. The block offset is the number of bits necessary to enumerate the set of contiguous memory locations. Yes. If the block size is 64 bytes, then this is 6 bytes. 6 bits. So all the data of a given block are contained in one cache entry. I hate this. The tag and index fields have the same meaning as before. It will present general expressions. Okay. What be the number of bits? So B, what is lowercase b? B is the block size, lowercase b is the amount of bits it needs. Oh, okay. L, what is L? L, the number of lines in a direct map cache of size S. Yep. That's, makes sense. N is log base 2 of L. What is N? The cache index. I agree. T is equal to A minus B plus N. So the B plus N term does what? So what is A first off? A is the number of bits in the memory address. Oh yeah. I mean, you need so many bits to, because like T plus N plus B has to provide the memory address. So it's going to take the same amount of bits because you have the same amount of locations. So that makes sense. So we're adding a mux with a black offset selector. Sounds good. I don't like these problems, but I'll still do it anyways. Multi-word direct map cache. Data size 64 KB. 32-bit byte addressable. Memory word is 4 bytes. Box size 16 bytes. Write back policy with 1 dirty bit per word. How does the CPU interpret the memory address? Well, you have 4 bits for the block index. $4096 cache lines. 12 index bits. 16 tag bits. So each data has 16 bytes. Why does it have 4 dirty bits? Because each memory word contains 4 bytes. So the space requirement for the metadata is just minus the data. Yeah. Space overhead. Metadata divided by total space. 14%. You're always trying not to fall asleep when reading this book. At least this chapter. This just feels like a repeat of the memory management chapter, dude. It's instructive to understand the point, the impact of increasing block size and cache. Exploiting spatial locality is the main intent of having increased block size. For a given total size of the cache, we would expect the miss rate to decrease with increasing block size. That makes sense. In the limit, we can simply have one cache block whose size is equal to the whole size of the cache. With a miss rate PD decreasing forever with the overall performance of the processor. I mean, I think that miss rate will keep. The miss rate will go down as you increase the block size, but it doesn't. You're still going to have to index into that. Really. How are you going to miss if everything's in the cache? Wait, is that right? How are you going to miss if everything's in the cache? If your block size is bigger than your memory, everything is going to be in your cache and you'll never miss. Am I bugging? I agree, maybe like the time, like the penalty would be larger. But I'm not certain that the amount of times you miss would not decrease from. Because how are you gonna miss if all your references are in the cache? Okay. If the working set of the program changes, then the large block size results in increasing the misrange. Oh, you're talking, okay, block size. That's fair. So it's not actually increasing the size of the cache. Okay. To answer the second question, so the second question, will the overall performance of the processor go up as we increase the block size? Probably not. Else we just wouldn't use cache in the first place. Flexible place. Book is such a snoozer, dude. 200 millis of calf can't even keep me awake for this book, man. How do you know which hit? That associative. Degree of associativity is how many different cache blocks it can be. Send it. So here we have a four-way set associative cache. So given a tag index and a byte offset is an index within the cache. An index is a byte offset is not an index. This is an index within a block. This is an index within a cache. And this is 20 bits. Why is it not 2 bits? What is it going to besides just choosing these? V. 20 bits. Oh, is that 1024? Why is that 20 bits? Is it not literally just... Or it should be 0 to 1024. Right. Is it 20 bits? Yeah. We've been over this. So if there's one parallel hardware for cache, then it's direct mapping. There's n, it's fully associative. Okay. Number of data blocks in the cache is the total cache size divided by the block size. I agree. The cache size divided by the degree of associativity times the block size is equal to the is equal to itself. Okay. Skipping those. Instruction and data caches. Dude. Snoozer, bro. And a little tree trimming. Now, shout out Christmas. I'm a big fan of like this time of year. Big cold head. It's also like my birthday time. It just goes like straight from like birthday, like nice weather, Thanksgiving, Christmas, New Year's, in like 2 months. And then that's the other 10 months are just absolute trash. It's kind of insane. In the processor pipeline, we show two caches. So yeah, the instruction and the data. Would it? Is that true? If your blocks are huge, maybe, but if your code is in the static memory and your data is above it, I feel like that would not fit in one block. How big? How big are blocks in like L1? 64 bytes. Okay, that's pretty small actually. Bigger blocks not so. They're all 64 bytes. How big are blocks in like DDR3 RAM? Maybe that's a bad question. Modern memory. Page size is 4 kilobytes. Multiple read ports to the caches to get around the structural hazard. I guess that is a good thing, and those are really intuitive to me. Primary design consideration is having the L1 cache match the hit time to the processor clock cycle time. Excuse me. iCache does not have to support writes. That is convenient. So you do have a unified L2 cache. Huh. But if it's 64 bytes, I'm surprised to think that the spatial locality would matter. $32 bits. Right, it's gonna be 64-bit. Am I dumb? I'm gonna ask that on Piazza, bro. Put that on. I don't understand that type. Yeah, you're gonna have your So this is my question. So the textbook claims that it is tempting to combine the two caches and make one single large unified cache. But if programs are stored with static vars and instructions at the bottom and heap and stack at the top, wouldn't the block size have to be quite large for this to be tempting? And then I just like looked it up. The common block size is 64 bytes. Then if my CPU has 64-bit instructions and data, like how are my data and instructions going to be in the same block? Hopefully that's not like a hella dumb question, but I need to scroll back up to answer somebody else's question. I think this is fine. Is this correct? Block size in bytes is 2 to the number of offset bytes. Or it'd be 2 to the number of... Yeah. Block size in bytes. Let's see, textbook page 926. So yeah, the block size in bytes is 2 to the number of it. Inverse of log base 2 is 2 to the... right? Inverse of log 2 is 2 to the x. If that's wrong, I'm literally jumping out the window. Can't wait. Alright, we haven't gotten to that chapter yet. So I'll keep this over here. Alright. Where were we at? Miss penalties. Oh, are you? Okay, I haven't got to that yet. Okay, yeah, it was this time. So now we're talking about reducing the miss penalty. The service time for the data transfer from memory to cache on misses. True. So it's different for reads and writes, and the penalty depends on other hardware such as write buffers. Usually the main memory system design accounts for the cache organization. In particular, the design supports block transfer to and from the CPU to populate the cache. Block transfer, okay. The memory bus, that's going to be huge. The memory bus that contains the main memory to the CPU plays a crucial role in determining this. Bus cycle time is the time taken for each data transfer between the processor and memory. The amount of data transfer in each cycle is the memory bandwidth. Memory bandwidth is a measure of the throughput available for information transfer. Bandwidth depends on the number of data wires. Depending on the width of the bus, the memory system may need multiple bus cycles to transfer a cache block. So yeah, if the block size is 4 words, and the memory bus width is 1 word, it's going to take 4 bus cycles. As a first order, we may define the miss penalty as the total time and CPU cycles for transferring a cache block from the memory to the cache. Or at least the read miss penalty. Right? However, the actual latency experience for the processor for an individual miss may be less than the block transfer time. This is because the memory system may respond to a miss by providing the specific data that the processor missed on before sending the rest of the memory block that contains the missed reference. Okay. So, despite... I didn't know you could just do that. Just like start a sentence with despite comma, that's kind of dope. Such block transfer support in the memory system. Despite... So, I think this is unintentional. Despite such block transfer support in the memory system, increasing the block size has other adverse effects. The processor incurs a read miss on location X. The cache subsystem initiates bringing in the whole block containing X, perhaps ensuring that the processor is served with X first. Depending on the bandwidth available, the memory system may be busy, yeah. So, yeah, that makes sense. In the meanwhile, either way, the processor may incur a second miss for Y in a different cache block, and now you're blocked by all the like the long blocks. You're putting stuff you don't need to read in there. No, the memory system cannot see, yeah, so it's gotta wait on X. You can't just focus on the miss rate to determine the cache block size. It's the classic tension between latency and throughput. We'll see it in the context of net. Okay, that's the next chapter. I think that's the next one I'm reading. Just check this. Hey, let's go. Cache replacement policy. So, temporal locality consideration suggests using a least recently used policy. For a fully associative cache, the cache chooses the replacement candidate, applying the least recently used from here on out LRU policy across all the blocks. For a set associative cache, so yeah, fully associative you can replace anything. Set associative you can only replace something else that shares the same set. Or shares the same. I imagine like if there are like unique sets that overlap, then but either way, whatever I'm saying. To keep track of LRU information, the cache needs additional metadata. So you're gonna need as many LRU bits. I guess it depends on what type of LRU you do. So we have hardware and a two-way set associative cache. Ah, that's kind of big brain. That's kind of huge brain, bro. Oh yeah. Tells you the most recently used. You need an ordering vector. What is an ordering vector? C1, C3, C0, C2. The ordering for set S0 shows that C2 was the least recently used. C1 is the most recently used. The decreasing time order of access. S0 is C1, C3, C0, C2. At this time, if a block has to be replaced from SRU, then the least recently used victim will be C1. Oh, it's so the other one. So, okay, it's C2. The CPU decreasing time order. Decreasing time order. I thought if it was decreasing time order, then this would be first. Because it's just decreasing in like the time since it happened. Perhaps that's the other way. Each row shows how the candidate for replacement changes based on the currently accessed block. So in this setup, if you try to access C1, then you're replacing C2. If you try to access C2, you're replacing C0. Access C2 again. This is just updating it. C1. Compulsory misses because the first time. AKA cold misses. So if the cache is full, then you gotta mix something. That's a capacity mix. Conflict miss is just in a set map. That is a conflict miss. I don't understand capacity miss. I'm fine with that. Integrating the translation look-aside buffer and caches. That is true. I kind of forgot about that. Who are the 12 indexes into a page? The rest. Let's go back to the page. So 52. 512 is equal to 9. The TLP. Number of tag and the TLP. Number of tag bits per entry. $12, right? Huh? I don't really understand this right now. Number of bits needed to store the page frame number in the translation look-aside buffer size of the PFN. Page frame number is 32 bits. Minus. Dude. What is a PA? Physical address. It's a lot of calculations. I think on the test I can just have like my formulae. Dude, I'm really curious what the answer to this is. So I'm just gonna skip that. Virtually indexed, physically tagged cache. I feel like I need a refresher on like virtual memory. How do you just go to YouTube?
We've got our virtual address, we've got a page offset and a virtual page number. We're going to use our TLB, which is going to have a tag and a physical page number, to translate the virtual page into a physical page and give us our physical address. So let's go ahead and get started. Here's a virtual address that comes in. We look at the page offset. The page offset is just going to go right through. And we have a virtual page number. The virtual page number is going to be translated. So the page offset just gets passed through. The virtual page number is going to go into the TLB. And, well, there's nothing in our TLB yet. So it's not in here, so we missed in the TLB. Now we need to go look up in our page table in order to get it. So we're going to have to go load from main memory to get our page table. And here's our page table, and it's in main memory. Now remember, the page table has to stay in main memory all the time, or we'll never be able to access anything. So we've got this in main memory so we can access it. Now we go ahead, we look up in our page table here. We want to find virtual page 3. So here's our page table. We're going to go down and look at page 3 in our page table. Here's the physical address or the physical page number we need. So we go ahead, we fill this into our TLB. So it's page 6, physical page, and our tag is 3 because we're looking virtual page 3 maps to physical page 6. Now we've loaded this into our TLB, and now we can go ahead and do our translation. So here we get our physical address. Now, here comes another one. So here's our virtual address 0003208. So again, we've got a page offset and a virtual page number. Page offset goes straight through. The virtual page number is going to go look up in the TLB. This time we're going to have a hit in the TLB because we actually have an entry for this. So we'll get the translation immediately. This is the best case. We found our virtual page in the TLB and we immediately got a physical translation. Here's an example of missing. So we go to access this virtual address here. Now the page offset's fine. Here's our virtual page number. Page offset goes straight through. The virtual page number goes to look in the cache. Well, sorry, not in the cache, the TLB, which is a page table cache. We look in here, it's not in here, so we're going to go over to memory and load this. We go to our page table in memory. We're looking virtual page 5, so we're going to walk 5 entries into our page table. Here's our translation. We take the translation, move it into our TLB, set the tag correctly so we know which virtual page this refers to, and now we can do our translation. So here's an example. We have a hit in the TLB. So we're going to go ahead and access this address here. When we run this address through the TLB, we find, hey, the data's in here. Great. So we've got our data. Now let's see what happens with this address. So here's a virtual address 4200. So our page offset's 200 and our page number is 4. So the page offset goes right through, and the virtual page number is going to go look in the TLB, but we don't find it in the TLB. And our TLB is full. So we're going to have to figure out which one of these entries to kick out. So in this case, we're going to kick out the one that we used least recently. Remember, we just used this entry, so we'll control page number 4000086.
Virtually indexed, physically tagged cache. Virtual address is a virtual page number and a page offset. It gets mapped to a physical frame number because of address translation, so this happens either in the TLB or the page table. However, the page offset part remains unchanged. A direct mapped or set associative cache derives the index for lookup from the least significant bits of the physical address. If we derive the cache index from the unchanging part of the virtual address, then we can look up the cache in parallel with the TLB lookup. Okay, that's kind of clean. Uses the virtual index that derives the tag from the physical address. For example, if the page size is 8 kilobytes, then the cache index is at most 13 bits, and typically less since part of the least significant bits specify the block offset. Okay, so it's 13 minus the amount of minus the log base 2 of the block size. Increasing the set associativity allows increasing the size of the cache. There is a limit because of hardware complexity. A partnership between software and hardware helps in eliminating this restriction. Although the hardware does the address translation, the memory manager is the software entity that sets up the VPN to PFN mapping. The memory manager uses a technique called page coloring to guarantee that more of the virtual address bits will remain unchanged by the translation process by choosing the VPN to PFN mapping carefully. Page coloring allows the processor to have a large virtually indexed physically tagged task independent of page size. So you have the virtual page number and the page offset. The TLB turns it into a page frame number, whereas the index is used in the cache. The index is used as the tag cache. Another way to get the translation out of the way is to use virtually tagged caches. That was kind of a lot. Hopefully this chapter is about to end. Doesn't look like it. Alright, I got a lot of reading to do. It's It's about time for my office hours. Alright, we're gonna finish this chapter. Hold on. I gotta do my punt engine office hours in like 5 minutes. Discord. Left. Let's pin it. Open. So is it parallel? Yeah. So I'm in the Discord. So, okay. I left off on 952. How much was left here? 12 more pages. So we'll finish this. And then I gotta read the TCP chapter later. 942. Was it 952? So let's recap cache design considerations. I know I changed some stuff. That's right. That works. That's good. Okay. So thus far we have introduced several concepts and it will be useful to enumerate them before we look at main memory. Spatial and temporal locality, hit, miss, hit rate, multi-level caches, direct map caches, read and write algorithms, spatial locality and block size, fully and set associative caches, IND caches, cache replacement policy, types of meshes, TLB and caches, cache controller, virtually indexed, physically tagged caches. That was kind of a lot, to be honest. So most modern processors have on-chip TLB, L1, and L2 caches. TLB and L1 is to reduce hit time, so they're simpler. TLB is quite often a small, fully associative cache with address translations with 64 to 256 entries. Split into a system portion that survives context switches and a user portion that is fetched upon a context switch. Some processors provide process tags in the TLB entries to avoid flushing the context switch time. L1 is optimized for speed of access. Usually it's split into IND caches employing a small degree of associativity, usually 2. Really? And the size is relatively small. Typically less than 64 kilobytes. L2 is optimized for reducing the miss rate. Usually it is a unified ID cache. 4, 8, even 16 way. A larger block size. L2 cache size for processor circa 2008 is the range of several hundreds of kilobytes to a few megabytes. So I just answered my own question. Well, that's the cache size, not the block size. So most also have a larger off-chip L3 cache, even larger in size. So I don't think I answered my question because it's still not the block size is still not that large. Main memory design considerations. The design of the processor memory bus and the organization of the physical memory play a crucial part in the performance of the memory hierarchy. As we mentioned earlier, the implementation of the physical memory uses DRAM technology that has a 100 to 1 speed differential. Really? 100 to 1. Wow. In the spirit of the textbook. In the spirit of the textbook in undertaking joint discovery of interesting concepts. Huh? We will start out by presenting very simple ideas for the main memory system. At the outset, we want the reader to understand that these ideas are far removed from the sophisticated memory system that one might see in a modern box. Let us consider 3 different memory bus organizations and the corresponding miss penalties. For the purposes of this discussion, we will assume that the CPU generates 32-bit addresses. The cache block size is 4 boards of 32 bits each. Simple main memory. Figure 936 shows the organization of a simple memory system. So we got a address bus at data bus. Cache writes data to the data bus. The CPU writes the address to the address bus, and main memory interfaces with both of them. CPU, so makes sense. DRAM access time 70 cycles. Bus cycle time 4 cycles. Block transfer, block size 4 words. So didn't we say that 4 words, so bits is 32, so this is 1 word. So it's going to take 4 cycles. And we're doing that 4 cycles. DRAM access time is 70. That is really trash. I didn't realize it was that slow. That's kind of crazy. 300 cycles. Wait, so I got 280. Where'd this come from? Data transfer from memory to CPU. Oh, it's got to go back. 4. Four cycles. Putting all the addresses in there and putting them back. Okay. Main memory and bus to match cache block size. So the data is 128 bits because it matches the cache block size. So to cut down on the miss penalty, we could organize the processor memory bus and the physical memory to match the block size. Okay. So all 4 words are now a single row of DRAM at single block access. Significant hardware complexity. Assume that the DRAM access time is 70 cycles. Assume that the bus cycle time for that is 4 cycles. So in this one, it's going to take, stop looking at the answer. DRAM access time is 70 cycles. Assume that the bus cycle time is 4 cycles. The block transfer time. So to transfer a block, it's going to take 4 to get there, 74, 78. I'm goaded. Interleaved memory. So the increased bus width makes the previous design infeasible. So you can do this with memory interleaving. So what is memory interleaving? So we have the cache and we have the CPU. CPU sends the address to 4 memory banks. And the 4 memory banks are buffered to the single data bus. So are these replicas or what are these? Each bank is responsible for providing a specific. Whoa, oh, really? They split it by word. That's kind of crazy. That's kind of smart. No, that is better. That is kind of smart. Banks take turns sending the. Oh, I thought they were gonna reconstruct it. Yeah, I guess the 128-bit doesn't work. So the 70 is split up, but you still gotta do the 4, 4, 4, 4. The interleaved memory system focuses on the fact that DRAM access time is the most intensive part. Yeah. So assume that DRAM access time is 70 cycles, bus cycle time. So get the address there 4, and then 70, and then 4, 4, 4, 4. So that's what, 20 That's 90. Goated. Keeping the processor busy is the most important thing. Get the data quickly as possible. It's not too different. So, what's the difference in modern memory systems? They're a far cry from what we just said. Not even interleaved, that's a relic of the past. So now it's inside DRAM chips themselves. DRAM chips pack 2 gigabits in one chip. DRAM chip that's 64 by 1. 6-bit address, 1 bit of data. Each bit of the DRAM storage is called a cell. They're arranged in an array. The 6-bit address is split into row addresses I and column addresses J. To access 1 bit out of this DRAM chip. This is kind of complicated. Dude, so you split the 6-bit address into rows and columns, indexing a matrix. Pulls the whole row. Then you select a bit with a column. So first off, I'm going to see modern, if this is on the test. Probably not. Oh, wait, what? We're not even on the TCP jumper. So I'm not kind of try too hard to understand this. So I'm just gonna double check we don't need another DRAM jump. Or the core. Or cells, my bad. So yeah, I don't really care about that. Performance implications of memory hierarchy. Let's see. So CPU registers, you got 8 to 32. This was written in 2008. Usually immediate access is 0 to 1 clock cycle. You knew it in 0 clock cycles? Maybe I'm dumb. L1, 32 to 128 kilobytes. 3 clock cycles. L2, 128 to 4 megabytes, 10 clock cycles. Main memory, 4 gigabytes. You bugging on me? Nah, it's 100 clock cycles. Virtual memory, a lot. Thousands. A nice summary. Spatial locality, contiguous memory locations, temporal locality, reuse of memory locations already accessed. So you have some cache organizations. Direct mapped is just a one-to-one mapping. Fully associative, you can go anywhere. And set associative, you can go to a set F places. Cache reading and writing. So you have a read hit and a write hit. So that's when you successfully read and write from the cache. Read miss and write miss. That's when you have to access memory to read and write through the cache. Write through is when you, every time you write to memory as well. Write back is you have like dirty bits and you only update on replacement. Cache parameters. So the total cache size, that's just the data of the cache in bytes. The block size is the amount of contiguous data in one data block. Degree of associativity is the amount, it is the size of the sets. Yes. Number of cache lines. It's the total size divided by the degree of associativity times the block size. I agree with S over B. I'm trying to figure out why it's the P is on the bottom. Because I thought you'd be replicating. Or no, because you have so much cache size. So that's split across P, like replicas. Divided by B. So I guess this is like unique cache lines. Okay. Cache access time, the amount of CPU cycles to check hit or miss in cache. Unit of CPU access. Size of data exchange. Unit of memory transfer. Miss penalty. Time and CPU. Index. It's the log base 2 of L bits. Block offset. Log base 2 of B bits. Tag. Yeah, that's just the rest of the bits. Cache. So valid bit, if it's valid, dirty bit signifies that it needs to be written to memory before replaced. Tag. Indexes. A. Data is a data. Hit rate. How many times you hit, miss the inverse. Other average memory stall. How many clock cycles does it take? Oh, never mind. This is the misses per instruction times the miss penalty. Effective memory access time at level I. Something. I'll figure that out later. Effective CPI is the average CPI plus the memory delay average. Memory stalls average. Compulsory miss, you never read it to begin with. Conflict miss, your index in the cache has been replaced. Capacity miss, the cache is full. FIFO. So LRU, you replace. So if you have like all these sets, you're replacing the one that was used least recently. FIFO, you just replace. Yeah, I know it means first in, first out, but what does that look like? Oh yeah, so first in, first out is based on like when it was entered in the cache, whereas least recently used is actually updated every time you reference it. SRAM, DRAM. See, I'm not too concerned with that. Review questions. Okay, so the next thing I need to read is the chapter on, so what is this here? Linked allocation. So this looks like file systems. Okay, so not file systems. We skip to parallel processing. This is multi-threaded programming. So hopefully this is not a long chapter. 12.2, 12.3, 12.32, 12.41. Oh, this is all. This might be one of the longest ones. 70, 74, 82. That's a 100-page chapter. That's gonna take like 2 hours to read. Oh, rip. Because even that one I just did, how long have I been doing this? That took an hour and a half. Oh, no way, I'm on the bathroom screen still. No, dude. That's tough. Yeah, I'm a little dumb. Rip. Alright, so I'm done reading that. I'm gonna do my contingent office hours, work on the Verilator stuff, then I'm gonna eat. Then I gotta do my Clash audio junk. Yeah, I got a lot to do, bro. Let's close that out. Curious if anybody answered this. Appears not. Still leave it over here. So we'll come to this chapter. I think like 480, 480 maybe? That's way further. 600. $610. 13.5. I think 510. Oh, shout out Ada, bro. Some old head. So. I might just continue reading this. I'm gonna give some more water while I consider that. So I need to read this before tomorrow. So I'll be able to recap it before tomorrow. I need to do the Flash audio stuff for like 5 hours on that. This is a long chapter, man. So let's spend in like an hour or two on Prompt Engine, and then I'll go back and do. So we got to make this work. So I left off. Let's go to GitHub. So issues, these are all me. So add Verilator test to CI. So yeah, that'd be good. So, in here, we have this make file. So let me just look up like Verilator. How do you, not even the project file structure is like Verilator in general. How do you use this junk? Because I tried a Jippity, didn't work. So Verilator documentation. This text is microscopic. The manual is a PDF. Yuck. Learn Verilator. It's Verilog to C++ compiler. User guide. This is what I'm looking for. So, verilating. System C. What is System C? So I'm really looking for this. Alright. So I wrote this test bench. Or more like I just generated this test bench. It does something. So what if we just do make right now? What if we end in here, then here, ls, cdhdl slash sv slash moving average make. No, I don't make that. This makes Verilator a model and runs coverage. Okay. First, I'm gonna make sure this works with Verilator. Dude, what? Just downloaded this. No, I downloaded this yesterday. What is going on right now? Verilator. Q. Make. Miss Simex. CPP test bench. Alright, I'm just going back to GPT, dude. I feel like GPT is actually good at this. So let's just try a naive solution. Or a lazy solution. I don't think you have to type any C++.
So first I will create a module called test that just runs hello, and then I will also create a basic test bench that just instantiates this module and then exits after one time step. All right, and next
Dude,
we will compile
whatever
our
video
design
player
using
Chromium
Verilator.
uses is
To do this,
garbage.
you just type in Verilator ----
Here's my
binary to
operating system.
create an executable, and then we can put in our source file
Verilator
names, so
dash binary
test.sv and tb.sv, and then we need to include
Top
---- top and then tb, because in this case the top level module is tb, and then it compiles, and then now we can run the converts. Incredibly useful aspect of Verilator, because now you can potentially interface with.
I think I'm showing there. So what is GPT? Why is it writing C++? I thought this is what Verilator does. It generates this. Yeah, what is that? These headers aren't even real, bro. GG, BGP, make. Yeah, she's just gonna come with a CPP. Is this really not this easy, dude? This is so dumb. Cannot find verilator.standard. Already done this. Can I find verilator._standard.sb? User bin verilator. I just need to clone it. In user share. CD user share. Clone. Oh my god. How do you install it? Dude. I think I have this. Give me C++. Autoconf. Export PWD. Slash config. Okay. Type make. Do I need to type make? Hopefully I'm not getting fork bombed right now. I kind of just press buttons. What's going on, dude? Just compiling these objects, including objects. Dude, this might be the longest build I've ever seen, bro. That's actually super false. Linux build is insane. Gotta take a nap while this is compiling, bro. Linking, okay. I consider that progress. Dude, this is crazy. Bro, what is going on right now? I swear I just compiled all of this. This is v3.0. This is actually insane. Alright, I'm taking a nap, bro. No way. You're trolling me, dude. Oh my. All that in an error, bro. You're actually trolling me right now. Dude. Right, at least now it looks like it's actually doing something. Error, no such file directory. Dude, what? Alright, I'm gonna just act like it works. That is ridiculous, bro. Plus DN. Yeah. You gotta open a website to go to the error, bro. What is this shit? I'm gonna go to the bathroom. Honestly, might not use Verilator and just use like Icarus or something. That's just so AIDS. I forgot. How could I forget that, bro? Little plant Lado. Типа щица. Now my green onions are going crazy. You can say what you want. You cannot say my green onions are not growing. Хорошо. All right, so what's wrong with this? So, D out is an input? That's definitely not intentional. Make. Next. Operator sub expects 19 bits on the right-hand side, but array cell generates 16 bits. Ah, we got the LSP here. Add expects 19 bits on the right-hand side. So the accumulator has width, ACC width, so it's data width plus n. And then the right-hand side is DN is 16 bits. That is true. Can't lie to you. So this is gonna be a Jippity type question here. You bite. I've been writing a lot of VHDL. So if this was in VHDL, I'd probably just do others. I'd do like the others 0 junk. Curious what Jippity thinks you should do here. 0 viewers. Are we still consistent with it? Shout out Delusion. Huh? Not the comment. Give me that link. CMake hello system C. I imagine that's what a C is. CMake hello C. Fine, try and see. Though, where is the Verilog file? Question for another day. Oh, so this is doing the simulator job. So what's the problem? We got to sign extendum. So I'm gonna just trust that. Give it a seems legit. Then at the bottom, E out. Got it? So we have use timing or no timing. Use timing or no timing. So So now is where I'm about to run out of one. Shite. So in this example, we make a new verilated context. Get the arguments. Construct VTOP. Evaluate until finished. Clean up. Destroy the model and return 0. Sounds reasonable, to be honest. Like, maybe we should make a... So... that sounds kind of reasonable, to be honest with you. So it wants a test bench.c++. So let's just act like that exists. But let's just blindly copy paste this junk. See if this is really worth anything. pb.cpp. It's just trace. Huh. Oh, yo, it is shit. Ooh, that's all right there. And let me make it. Did that do something? Let me run it. And then we view the waveforms. And I'm downloading GTK wave. And I download its dependencies. The computer, let's go. No such VCD file. So where's the waveform? So CD object dir, then do this. OS. Where's my waveform at, bruh? Where's my waveform at, bruh? Shit. Object dir. Average accumulator. LS. So let's go back to NVM. Where is my little waveform, bro? So I should probably .get ignore any obj dir. Probably be kind of intelligent. We can do later. It's gonna be obj dir. So is that now? Yes. Okay. So the test bench. If you have tracing enabled, can you make a makefile that does the tracing and such? It should have some assertions, so I can run it CI and validate she. So I'm actually impressed. Jippity didn't just brick my whole operating system and actually did something productive. Shout out Jippity. Three hours in. Hit another zoom on this. I think it's... I'm curious on my phone, like, can you read this text? I'm in the terminal. SIPA. DoorDash. Dude, that is so annoying. Let's say you can read the text. It's passable. Трансляция. Data is our freaking fire alarm thing going on? 5 responses? Scheisse. So that's a lot longer of a test bench though. So hit blindly copying this into here. Looks awesome. So it appears that this doesn't even exist anymore. Kind of for the better. There's a little bit less entropy in the repo. You'll have to see it. So no vec, no vec. I have vec. Shimmy. Shimmy, ma. Make. If this works, I'm gonna. So okay. That's recoverable. So I renamed it to TB. We survive this. N equals 3. Range. No. So. N equals 3. So something's definitely wrong there. It's here. N equals 3. Here, N equals 3. Hmm. So really not messing with the N equals 3. So let's harpoon some junk. Let's harpoon this, then let's go to tb.cpp. Let's harpoon that. So this N equals 3, it's really not messing with that. That's from the, that's a command. N equals 3 parameters. So I'm just gonna parameters N equals 3. So it thinks that that is a parameters. Honestly, Verilator. You gotta mark it Verilator public. Parameter. Verilator public. Will this do anything? If this does something, I'm gonna be quite impressed. So, back in here. Just put that back. Cannot find file containing module N equals 3. Dash G. Verilator dash G. So dash G for global. Dash G. Dude. How is there literally nothing on the whole dash G option? Name equals value. overwrites the given parameter of the top. So top module. So must it be capital? Could be something, because it's also not liking it in the OSP. And 2. Two should be N2. Should be N2. Should be N2. Should be N2. Let's try that. N equals 3. Can you not make a variable named N? Let's undo that. What are those comments? Let's make this K. Let's make this called K. Hex, but I don't know. Why is it? It's not liking the K equals 3. K equals 3. So Verilator flags. Parameters. So let's do parameters and then Verilator flags. Parameters. Verilator flags. Thinks I'm passing a file. Dash G. So maybe this is not a thing. So we're just gonna straight up delete that. Okay, now it's so we have an error. No such file or directory. OSP being shite there is kind of annoying. No such thing. Cannot open file. V moving average accumulator. No such file or directory V. Obj_dir moving average accumulator. V moving average accumulator. so I think it's looking for the moving top module. Is it this .mk? So is it thinking that okay is there? Objector. Trying to see, is it because it's not in the right directory? Entering directory objector. So now it's running the TG. Entering directory objector. Cannot open. Accumulator.mk. LD. Accumulator.h. What does LD do? It's a linker. Moving average accumulator.mk. Dot D. The top module. Moving average accumulator. Kind of aids. Cannot find object or slash moving average accumulator. Do the commands. So that works. So what's the difference in this command? Make, so let's first do the dash J part. Object dir dash F, moving average accumulator dot MK. And we throw in V top module. Make. Okay. So now it's just the program being messed up. Mismatch at time 10. Slash object slash view. Mismatch at time 10. Okay. Mismatch at times 10. Expected 1 got 0. OSP is tripping when I do this. Make, generate, control, commands, Verilators, Clang, OSP. Get Verilator depths in Clang LSP. Make LSP. You know what I'm trying to say? Make LSP Clang file. Oh my god, okay, I gotta go to GitHub. JD C M, and then in here is it, that's for CMake. Yeah, I'm sure. Object there, but it sees it. Why is this so AIDS? So what am I expecting? Sample buffer. So the problem is it's not actually. Is it supposed to be 1? What's the input? So this is the wire, 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 wire. So on the positive edge of the clock. So I'm just confused. What is the input here? The input is sim time. So reset is high. Sometimes it's forced to reset to 0. Okay, so provide input data. DM is good at input data. So input data is sim time. So it is time divided by 2 mod 256. Expected accumulator. Shift the sample buffer. Now put the new sample. What changed? Literally nothing changed, bro. Huh? LD again? Undefined reference. Reference domain. What do you mean, dude? Wait, why did it just work for like 3 seconds? Make LD. Return 1x it says. Everything is undefined. Reference domain. It's not the same command I just ran. Verilator. Make C. So the Verilator command isn't right, I don't think. Make Verilator flags is going to be -cc. That's just ESC, that's just trace. So Verilator. That's just CC. DT dollar. That's just CC. We can have the dash O in there. Verilog sources. It's top module.sv. D to the $sign. Paste it there. CC Verilog sources. --exe. Executable test bench. Just trace. So make clean. Make error 1. What's the difference? Verilator. Just a CC. Moving average objector. Honestly, delete the objector doc. ET dash. It's the same thing. Make clean. Time 10, expected 1, got 0. DMA web test. So here we're gonna have another job that is moving accumulator test. So even if it just fails, latest steps. So we can do just name checkout code. Check out that BC. Install dependencies. I don't think we need to update, we just need Verilator and make. What if we do make test? Make test. So first you got a CD in the right place. Animations are run, we're gonna do some guards. Or are these guards are just like line extenders. Run, so we're doing this. So this is gonna run at the top, right? So we got a CD HDL slash HV. Sorry, SV slash moving average accumulator. Waveform. That BCD. Add that to get ignore. GK waveform. Huh? So and that should be the workflow existing. Make test. Modify, make clean. Make test. Expected 1 got 0, so we can try it. Did add dash A. Yeah, git push. Might have to set up tree. No, I don't. So moving to moving average. Compare pull request. What run my new check? Let's just try it out. I think I just duplicated a bunch of crap. Moving average account untested. Remove proj. This one. This has one more PR, so should we get all get switch or get base. That's so annoying how they do this. It's Where's the issue, dude? So get ignore. Who cares? Dude, why the Dude, what do we change the So what are we there, dude? What the That's dangerous. Why is it not running this, bro? Dude, oh my god. What is different? Uses run. What do you mean? Uses run. Uses run. What are you talking about? Hmm. I mean, that's as expected. So that resolves number 24, 22. Doesn't it automatically close these? So that was just kind of rushed together, but I just wanted to make it exist. So the status on this one, ready. Call this a bug. Mm. So that was like kind of trash, but let's see. Going back to this. So at any given point, this should have the value of the 8 most recent samples. So we have an accumulator width. Data width plus k. when you do signed, so the way this works, you have the last n samples, and you sum them up, and then shift it so I feel like I should write about this. The way this works. So you have 2 to the k samples. So what does a circuit do? Takes in a stream and returns the average over the last 2 to the k samples. So internally, you can imagine 2 to the k is like a denominator, and the sum over the last 8 samples is like the numerator, and the quotient floored, or like the quotient is the quotient not counting the remainder is the output. So how do we effectively do this in a circuit? We keep a buffer. So if we actually just add the one in and subtract the old one out, then you're chilling. The problem is knowing. So the accumulator, we subtract in, subtract the oldest and add the newest. And we shift the sample buffer. And then we compute D out, set it to D out. I feel like this is right. So what do we do in TB? I'm confused. What is the input here? Can we just make the input data 1? So we should always output 1. Yeah? Let's try that. Time 20. Expected 1 got 0. Dude, these errors are making me rage, dude. Be moving over. So it would be nice. Then LD is fucked. But now we have this. So theoretically, in my test bench, dude, C++ include relative file path. Obviously, that's a Verilator model header. Data slash. So that's acting like it's slash data slash. See, why is it going with that bullshit? Objector. Dude, I'm convinced Clang OSP is dumb as fuck. It does not like having the object in there. Objector, even though it has objector in this. So even though this has objector. It needs objector there? Huh? What the heck? Not a single soul is talking about this. Could be two curves. Oh, EXP. Okay, this is good. I like this. Yeah, this is actually kind of good, bruh. Local param. ACC width. Is it N? It's probably the N that's messing it up, yeah. Local param variable. Local param style, name style. Camel case. When an unpacked dimension range is zero based. So what I just have a variable. So what does good variable look like? This was a Google repo? Huh. Variable style guide. Where's the style guide, bro? Name. So param, what are params supposed to look like? Data width. Data what? OSP rename. X. ACC width. See what y'all mean now. So local param start with capital letters. What about ACC? It's because it's not a local param. The K. That's pretty self-explanatory. So where am I saying K? So here it should be to the exponent. That was K there. All right, pop in energy drinks. It's making me that good of a plan yet, to be honest with you. Yeshuras. So I feel like this works. Not sure why the tabs are so off. Thought I had a formatter. Why are the tabs so off? Oh, maybe these are 4 and these are 2. Fair enough, I guess. It's not making sense to me, but jeez. My game. Okay. How does this divide? Huh. Huh. Accumulator from the width down to the exponent. So at time 20, it expected 1 and got 0. No, I did not mean uint64, dude. Sample buffer n. Initialize to 0, accumulator 0. Sim time. That's how many clock cycles we're doing. We're doing 1,000 clock cycles. Or top clock equals not top clock. So we're doing inputs on the rising edge. So the input data is going to be 1. If not reset, we do this. So we subtract the oversample, add in the new one. Shift everything over. What if we just had an index that tells you which one to write into? Instead of having a shifting everything, we just index into it with like a box. Yeah. Because here, this, what does this synthesize to? Instead of doing this, we could just have an intermediate index value. Wait, what is I? We could have like a reg. Int Verilog register int. Verilog integer. Integer. So it is the oldest element index of oldest element in sample buffer. So if reset, let me reset the sample buffer. But here, instead of shifting it, so we're going to subtract sample buffer n minus 1, data width minus 1. The accumulator. You ever figure out this? The instructor skipped it as well. Can we just stop working on this in a minute? Hit the sign. So you have n equals 1 as the exponent. Like we did with, so you have the accumulator. Let's sum with last n samples. Circular buffer storing last n samples. I'm not sure we need that. If reset, reset that. Then reset that, then bonus index. Index, we can put that as 0. Or is it just 0? 0 as well. Index. So we're doing some sign extension. So what is this equal to? ACC, we're signing it to ACC minus signed sample buffer oldest index plus signed in. Looks good. Then we get rid of this. Oldest index. Then we overwrite the oldest index. Then we increment I. Mod n. Looks good to me. That accepts 19 bits on the right hand side. Signed is generating 16 bits. The accumulator is 19 bits. This is 16 bits. I'm Steve. They did it for me. I trust it. It's not too difficult there. I want some updates to the make file. That's not gonna work. Almost like this was here before. So this is like the length, ACC minus data width, sample buffer, at oldest index, data width minus 1. I'm expecting it to be like so let's just see if it's gonna be 0 the whole time. 14, I got 1. So what if we just fill it in with 1s? Expected 1 got 0. The input data 1. Just fill this with 1. So the only input going into it is 1. Well, yeah, because this is. So what if I don't want to count the resets? It's the resets messing it up. So if it's 2, it works. Simulation completed successfully. It never throws this. Mismatch at time. It always matches. So let's consider this. Choose the inputs. Match SV files params. So we know that, we know that, we know that. We know that. 32 bits per number. And this one is so we have the sim loop. Toggle the clock and put some rising edge. Input data. Randomish input data. Date expected accumulator. Simple buffer. Subtract the oldest sample and add the new one. Replace the oldest sample with a new input. Update the oldest input circularly. Compute expected output. Repair and error if bad. Clean up. Clean up. And access. Link. Awesome, that works, man. I ain't even do nothing, type. Scheiße. So get checkout dash B. Move accumulator work. Get dash A. Get commit dash M. Fix move egg average and test. Get push. Get push just to set Stream origin. Contingent. This resolves. Number 26. See if this works. If this works, that's goated. Это работал? Ебать! Смотрите. Отлично. Oh, that's awesome. Dang, that just works. That's kind of insane. Alright. So I have a few other things to do. I'm supposed to be eating right now. I need to make sure my group submits my files. What's going on with that? Здесь это проект. Там что нового? Final edits будет 6 часов назад. Есть здесь от files. Ебать. Мне надо еще раз компилировать. Надо быть. Нам надо. Какой симулятор? Нет. Сов. Здесь будет, да? Это 6 мегабайтов. Да, я думаю, что это правильно. Нам надо... Ну. Здесь. Alright, that was dope. Nah, look at that languages, bruh. Nah, that languages is good. Nah, that's freaking crazy. Good. So, nah, this alone is good, dude. Haskell C, C++, System Verilog, Zig, TCL, and Makefile. That is such a nightmarish. You get tech stack. Now the kitchen sink tech stack is good, bro. Tell me that's not good. Alright, so I need to read this, make my Clash gain core work. Um, gotta submit the ECE project. So I read chapter 9 at the sequential. I gotta read gain builds, moving average account accumulator works. Gotta do the 2200 attendance quiz. Gotta do the extra credit. So the demo works. Just gotta submit it. So I'm supposed to be eating now. Then I'll do the EC. I'll have to read again. Probably do punt. Probably decrease my punt engine time. Eat that. Office hours over. Nah, this tech stack is freaking good, dude. Le cornichon. Alright. How long have I been doing this? It's been 4 hours. We don't stop now. Tell you that much. Don't tell me it's been on bathroom break the whole time. Oh my. Dude. Wow. How long has it been on bathroom break? Oh my god. Alright, so what oh my. So effectively what I did. That's so dumb. That's tough. Alright, so what I did, merged, fixed moving accumulator average, I can't even say it properly. So we got this test running on CI. Run simulation. Simulating completed successfully. HD. So what is the simulation? So we have these two. So what does this do? It takes in a number and outputs the average of that number over the last 2 to the exponent samples. So that works internally. We have a sample buffer, size n, stores the last n samples. We have an index that tracks the oldest ones, like every time a new sample comes in, every clock cycle, we increment the index, as you'll see here, and we modulo n it. And then the accumulator, you can think of this as like the numerator of the moving average. And so we subtract away the oldest value and then add in the newest one. And then we shift it. We right shift it by the, so you can imagine the size of the accumulator is going to be the 16 bits, which is the size of the data, plus the exponent, because like if you max out data width and multiply that by 2 to the n, the max capacity of that will be, the max amount of bits that will take will be data width plus exponent. And so we right shift away the exponent, which is effectively dividing it again by 2 to the n. And that's the out. And so we test it with this. Am I dumb? I think this doesn't actually work. I'm dumb. Oh my god. I'm really dumb. Wow, I'm actually stupid. Oh my god. Yeah, this doesn't work. I'm quite dumb. It never even goes into the main loop because of reset is 1. Dang, I'm special needs. So reset is 1. Then in here, if sim time is greater than 4, restop, reset is equal to 0. Time 10 got expected 1 got 0. Expected 1. Accumulator right shift exponent. Got 0. So can we turn on trace? Make trace. Make just no. What do you turn on trace? Trace. So it should be on. So what is that command? Waveform G form waveform. What is that junk called? G waveform G wave. What is it called? Oh my god. GFW. Right, it's like GFW wave or something. View waveform CMD. BCD. What is that giant called, dude? It's in my most recent commands. There's the G, so it definitely starts with a G. GTK wave. GTK wave. Huh. Why is it actually good? GTK wave. Waveform. WCD. No symbols in VCD file, is it? KMS. Make. Okay, this is so rage bait. Doesn't actually work, and I'm special needs. Top reset equals 0 reset. Subtract, so not top reset, accumulator 0. Subtract the oldest sample. Add the newest one. Oldest sample, replace it. The input data. Update it. Circular oldest index. Repeat accepted it. Accumulator, right shift, exponent. So top DN is equal to input data. 16-bit int. And then we do. The sample buffer is filled with 16-bit ints. The accumulator is 32 bits. So we're right shifting the accumulator by the exponent. Doesn't work. Time 10 expected 1. Got 0. So what if we just expect 0 all the time? So let's just lock this to 1. Time 20. We expected 1, we got 0. So after 20, time 20. Expected 1 and we got 0. Expected 1 and we got 0. Positive clock. So the positive edge of the clock. I would just view it. Delete the oldest fullest index circular. Oldest index plus 1%. Accumulator right shift. Exponent. Why is it different? Expected 1. Alright, I'm gonna have to just quit this for now. Got a bunch of other junk to do. I'm gonna end this. 4 hours. Like, we're